Good morning, esteemed dignitaries. The founder, President of JANARDAN Singh Foundation, Dr. Rajesh Singh Sir, the President of AIP, Dr. Sanjay Kumar Singh, the distinguished speakers of today's workshop, Dr. Manas Sharma and Dr. Mr. Kaushal Akeda, the colleagues, students, and my dear friends, a warm welcome to all of you to this insightful exploration into the realm of density functional theory. Myself, Sangamitra R. I am the Vice President of Student Chapter of Kerala. Currently, I am pursuing my MSc Physics second year from Vimla College, Autonomous Thrissur. I am basically a Keralite. I was a PTTS 2022 participant, Physics Training and Talent Search Program conducted by the Ahmedabad University. Now, talking about today's program, Mastering DFT, a hands-on training workshop organized by JS Foundation, Janardhan Singh Foundation, in association with Association of Indian Physicists. Janardhan Singh Foundation is a non-profit organization registered under the Ministry of Corporate Affairs, Government of India, dedicated in promoting education, health, social welfare in underserved communities. The foundational educational program, it aims to provide various new opportunities for youngsters of the nation by Association of Indian Physicists. They also collaborate with local schools and institutions to enhance educational infrastructure and support teachers, students, and alike. Now, I would like to introduce Dr. Sanjay Kumar Singh sir for a brief introduction of JSF and AIP. Over to you, sir.
Yeah, thank you, dear Sangmitra, Vice President of Student AIP Chapter of Kerala. A very good morning to everyone. I, Dr. Sanjay Kumar Singh, convener of this workshop and the founder president of Association of Indian Physicists. I'm delighted to welcome you all to the Mastering DFT Hands-on Training Workshop. So it is an honor to have such a diverse and enthusiastic group of participants, including undergraduate and postgraduate students, PhD scholars, postdoc, and esteemed faculty members join us today. Firstly, I would like to extend my heartfelt gratitude to the Patron-in-Chief, Dr. Rajesh Singh Sir, Founder President of Janardhan Singh Foundation, and the Association of Indian Physicists AIP for their unwavering support and collaboration in organizing this event. Their dedication to promoting education and fostering a culture of learning has been instrumental in making this workshop possible. The primary objective of this workshop is to provide an unparalleled platform for academic enthusiasts to explore into the fascinating area of density functional theory. Today, we have the privilege of learning from some of the most distinguished experts in the field who will guide us through the details of prominent DFT-based codes such as QUANTUM ESPRESSO and ORCA. Our first expert, Dr. Manas Sharma sir from University of Jena, Germany, will lead us through the morning sessions, sharing his extensive knowledge and experience with Quantum Espresso. Mr. Kaushal Akeda sir from the MS University of Baroda, Gujarat, will introduce us to ORCA software, guiding us through its functionalities and potential for research in the theoretical physics. I heartily welcome Dr. Manas and Kaushal sir. I also welcome my student, Mr. Nikhil Kumar from University of Jena, Germany. So this workshop is not just a series of lectures, it is an interactive experience designed to equip you with the skills and confidence needed to embark on your research journey. We encourage you to actively participate, ask questions, and make the most of the interaction session with our experts. Lastly, I want to emphasize the importance of continuous learning and collaboration. The knowledge and skills you acquire today are just the beginning. Beyond this workshop, the AIP Theoretical Research Team is committed to providing ongoing support and guidance, ensuring that you can confidently navigate your research endeavors. Thank you once again for joining us today. Let us make the most of this opportunity to learn, explore, and grow together. I wish you all a productive and enhancing experience. Thank you all. Over to Ms. Sangmitra. Thank you.
Now, I would like to introduce Mr. Kaushal Akeda, the chairperson of Gujarat chapter AIP, for his opening remark on this workshop.
Thank you, Sanmitra. So, Good morning, everyone. Welcome to our Mastering DFT hands-on training workshop. It's a fantastic to see so many dedicated individual here today. I got to dive into the depth of the density functional theory. So DFT is a cornerstone of the modern computational material science and chemistry, offering powerful insight into the electronic structure of atom, molecule, and solids. Whether you are here to refine your existing skill or to gain a new perspective, this workshop is designed to equip you with practical knowledge and hands-on experience. Throughout today's sessions, we will explore both theoretical foundation and practical application of DFT. Our goal is not only to enhance your understanding, but also to empower you to tackle a complex problem with confidence and precision. We are privileged to have a team of expert instructor who bring a wealth of experience and passion to the table. They will guide you through the intricacy of DFT from basic principle to advanced technique and help you apply this concept to a real world scenario. I encourage you to engage activity, ask a question, and collaborate with your peers. The knowledge you gain here is only as valuable the effort you put into it, and the collaborative spirit of our workshop will be a key part of your learning journey. Thank you for being here and for commitment to advancing your skill. Let's make the most of this opportunity and dive into the exciting world of density functional theory. Enjoy the workshop. Thank you so much.
Now, I would like to introduce Professor Dr. Rajesh Singh, Founder President of JS Foundation, for his remark by Patron in Chief JS Foundation.
Ladies and gentlemen, it is with great pleasure and anticipation that I welcome you to Mastering DFT, a hands-on training workshop. It is organized by JANARDAN Singh Foundation in association with AIP. The purpose of this workshop is to offer distinctive platform for academic enthusiasts, ranging from undergraduate and postgraduate students to Ph.D. scholars and faculty members, to explore the field of theoretical physics. The hands-on session with leading DFT-based codes like QUANTUM ESPRESSO ORCA, guided by esteemed scientists from India and abroad, you will acquire invaluable insights and practical skills. The Janardhan Singh Foundation has always prioritized education and research in physics. The training program exemplifies our dedication to providing practical learning experiences. By participating with the IAIP, we aim to equip participants with the skills needed to excel in DFT mastery. This event is not just about learning, it's about empowerment. Participants will gain the tools and knowledge to tackle the complex challenges and contribute meaningfully to scientific research and technological advancement. I am grateful to the collaboration with the AIP. Together, we are empowering the next generation of physicists to push boundaries and drive innovation. To the participants, I urge you to approach this opportunity with enthusiasm and determination. Mastery of DFT codes opens doors to new frontiers in science and technology. Embrace the challenges, embrace the learning process, and let your passion for discovery guide you. As founder president of Janardhan Singh Foundation, I am proud of the work being done by the Janardhan Singh Foundation and our partners. Together, we are shaping the future of physics, and I have no doubt that the impact of the training program will be felt to years to come. I extend my gratitude to all organizers, sponsors, and participants for their contributions. Your dedication to advancing scientific knowledge is commendable, and I am confident that together we will contribute to make great strides in the field of physics. Thank you, and many these training programs be resounding success. Thank you, and Jai Hind.
Thank you, sir. Thank you so much. Yeah, Mitra, there is a network issue. Hello, Mitra. Okay, there may be some network issue from Mitra side. So I'd like to invite Dr. Manas sir from University of Jena. Dr. Manas sir, we welcome you on this foundation platform. We are very grateful for you for accepting our invitation and for your providing your precious time on our JS Foundation platform. I hope our participants will learn from your expertise. As Dr. Manas has completed his PhD from Jena University, and he's a very nice, he's kind persons, and he's always available for helping the people. So, without taking much of time, I would like to invite Dr. Manas sir to take the charge, and I also invite Mr. Kausala Gida sir for chairing the session. Over to Manas sir and Kausal sir.
Hello everyone, good morning, and thank you Sanjay sir for the warm welcome, and please don't call me sir. Okay, let me go ahead and share my screen, and I hope everyone can hear me, right?
Yeah, right. So you are okay.
This one. Okay. Okay, so in today's today's lecture is going to be about density functional theory, and I'll be covering the fundamentals of density functional theory, and then I will briefly talk about some applications and also tell you about some advanced computational tools that can make your life easier when dealing with DFT codes. So the computational modeling of chemical systems is extremely crucial because it helps us understand molecular behavior and also predict molecular behavior and offer us insights that may not be easily obtained from experiments. And this is where accurate electronic structure calculations can help us understand how electrons are reacting to light, or design materials with tailored functionalities, or optimize a chemical process towards the desired outcome. Now, the choice of a computational method that you need to use is not really unique. So it's not just DFT that you can use to simulate a chemical system, but rather you have a variety of computational methods that you can use to simulate your material. However, the choice actually depends on the length scale, that is the size of the material or the chemical system that you want to investigate, or the time scale of the chemical process that you want to investigate. And of course, the computational cost of these methods depend on the level of accuracy. Of course, quantum mechanics is going to be the most expensive, while the classical approaches would be somewhat cheaper. And as I already mentioned, the choice of method would depend on the size of the system. And since today's talk is about density function theory, so let me say that it is a quantum mechanical method. So you are essentially solving the Schrodinger equation with some approximations, and therefore it is useful for very small systems that have sizes in the range of nanometers or angstroms. And as one can expect that at such small length scales, of course, you have to invoke quantum mechanical laws. So you have to solve the Schrodinger equation, and specifically the time-independent Schrodinger equation. And you are going to be applying it to materials that consist of atoms, and these atoms then consist of nuclei and electrons. Therefore, your Hamiltonian in the time-independent Schrodinger equation can then be written as shown here. So essentially, you have the kinetic energy of your electrons, you have the kinetic energy of your nuclei, then you have the electron-electron interaction term, then you have the nuclei-nuclei interaction term, as well as the interaction between the electrons and the nuclei. Here, Z represents the atomic number, or the number of protons in your nuclei. And this is something known as the many-electron or the many-body Hamiltonian. And solving the Schrodinger equation is our goal. However, okay. One approximation that is very popularly invoked then is to set the nuclei masses to infinity, because as you already know, the mass of a proton is approximately 2,000 times that of an electron. So what you can do is you can consider the this term that has the nuclei mass in the denominator, as well as this term to be 0. So essentially you will consider your nuclei to be fixed, and then you will only solve the electronic Schrodinger equation. And here this psi is the electronic wave function. So you just have the electronic kinetic energy, the interaction between the electrons, as well as the interaction between the nuclei and the electrons. So this would be attractive in nature. And yeah, so this is known as either the Born-Oppenheimer approximation or a clamped nuclei approximation. Now, why do you need to make approximations to solve the Schrodinger equation? Why cannot you solve it exactly? So I already invoked one approximation, that is the Born-Oppenheimer approximation, but even that is not enough. As you may know from your quantum mechanics course, that you can barely or like hardly solve the Schrodinger equation for just a hydrogen atom. And maybe by invoking some more approximation for the helium atom with 2 electrons, but beyond that, it's just not possible to solve the Schrodinger equation analytically. And that is because this wave function of your material, or the electronic wave function, actually depends on the positions of all the electrons, and that is because of this electron-electron interaction term. So you have Ri minus Rj, so each electron is interacting with all the other electrons, and therefore your wave function becomes a many-body or many-electron wave function. So each electronic position can be subdivided into XYZ components. So in total, you will have 3 n variables. So if you have n electrons, you have n positions, and then 3 subcomponents, the XYZ components. So you have 3 n variables. Now, okay, I said you cannot solve it analytically. Now you may say, okay, but then I will just solve it numerically. But even that is basically impossible to do exactly, because let us consider an example of the iron atom, that is Fe atom, that has 26 electrons. Now this wave function would now be a function of 78 variables, because you have 26 electrons and their XYZ components. So you have 78 variables in total. And when you're doing calculations numerically, you want to store your wave function, let's say, on a grid, because all numerical methods, you are doing some sort of discretization. So let's say you decide to use 10 points in each direction, and this is a really coarse grade. This will, of course, not give you correct results, but even if you're using just 10 points in each direction, you end up requiring to store 10 to the power 78 numbers. And let's say each of these numbers is stored using a double precision, and a double precision number requires 8 bytes for storage. Then that means that you will be requiring 8 times 10 to the power 78 bytes of storage. And actually, if you compare that to all the data that is stored worldwide back in 2020, that was just 64 times 10 to the 21 bytes. So it's, of course, it is impossible to store such a small wave function with just 10 grid points, even on if you consider entire storage in the world. So that is why the if you are doing solving the Schrodinger equation using the wave functions, it's going to be really hard. And this is somewhat where density functional theory comes into the picture. So instead of using this wave function, which is a function of 3n variables, you employ electron density, that is a function of just 3 variables. So here is an artistic representation of the electron density of the benzene molecule. And yeah, so the fundamental or the foundation of density functional theory is laid by the Hohenberg-Kohn theorems. And the first theorem states that there is a one-to-one mapping between the electron density of your system as well as the external potential. That is, you can consider that to be your nuclear potential. And this helps you come up with the Hamiltonian of your system. Then you can solve the Schrodinger equation and obtain the wave function of your system, and therefore the ground state energy of your system. And this energy therefore can be considered to be a functional of the electron density, because I said there's a one-to-one mapping between the electron density as well as the ground state energy. So the energy can be considered as a functional of your electron density, and it can be written as follows. So it is the expectation value of your wave function, of your Hamiltonian with the ground state wave function. So you have the kinetic energy, nuclear potential, and the electron-electron interaction term that we already saw earlier. Now, the second theorem provides a variational principle counterpart for density functional theory. So it states that for any given density, for any given electron density, the energy that you will obtain using this energy functional would actually be greater or equal to the ground state energy. So if you want to find the ground state energy, what you can do is you can vary the electron density, and the point at which you find the energy to be minimum would be considered your ground state energy. So it would be somewhat like an optimization problem. And the energy functional, as I already mentioned, can actually be written in a more simplistic form by saying that, okay, the energy, which is a functional of electron density, can also be written as functionals of subcomponents. For example, the kinetic energy as a functional of density, nuclear electron interaction term energy as a functional of density, and then the electron-electron interaction as a functional of density. Now, the electron-electron interaction term can actually be further broken down into 2 terms. So you have the Coulomb interaction or the repulsion between your electrons. So that would be one term, and this can be considered classical, because even in classical mechanics, you know that how an electron will be interacting with another electron in terms of the electrostatic repulsion. However, there would be one more non-classical electron-electron interaction that stems from quantum mechanics due to the fact that electrons are identical in nature and follow the Pauli exclusion principle. Now, so I said that ideally the the ground state energy can be written as a function of density, but that's not actually true. So that is the problem. So which of all these terms that I mentioned here can actually be written as a explicit functional of density? So the answer is that you can actually only write these 2 terms, that is the nuclear electron interaction energy as well as the electron-electron Coulomb interaction energy, in terms of the electron density, and the remaining terms, that is the kinetic energy and the non-classical electron-electron interaction term, can only be written in terms of the wave function. So that is a problem. So you may already know that the kinetic energy can be written as this, so del square psi, and then the non-classical electron-electron interaction can be written basically by subtracting the Coulomb interaction from the total electron-electron interactions. However, physicists are, of course, not going to stop at this problem. So we face a problem and then we come up with some solution, or at least an approximation. So what the physicists tried was to come up with an approximation. That is, they studied the uniform electron gas system, and they obtained the expressions for the kinetic energy in terms of the electron density, as well as the non-classical electron-electron terms in terms of the electron density. And this is only possible for this uniform electron gas system to have these kinetic energy and the non-classical electron-electron terms in terms of density exactly. And this is actually known as the Thomas Fermi approach, because you have this Thomas Fermi kinetic energy density function, then you have the local density approximation. And so they somehow came up with this equation. And the advantage is that, of course, it is only a function of 3 variables because it only employs density. However, when they applied it to a problem, for example, the nuclear structure of the argon atom, then the electronic structure of the argon atom, then they found that actually this, so this curve is from the Thomas Fermi approach, and it is not replicating this structure that is found in experiments or even with some other levels of theory. So this didn't really work out really well. Now, what is the solution? So the solution, the next step in density functional theory was provided by Kohn and Sham, which came up with the Kohn-Sham DFT. So whenever you are performing a DFT calculation with any code in the world right now, you are most of the time doing Kohn-Sham DFT. In some cases, you are doing the previous approach that I already mentioned, but most of the times you are using Kohn-Sham DFT. So it is important to understand this. So in Kohn-Sham DFT, you introduce a fictitious system of non-interacting electrons. However, they have the same density as that of your reference original system. And the reason this simplifies the calculation of kinetic energy is that we introduce orbitals now. So instead of just working with density, we invoke one more thing, that is the orbitals of your single electrons. So each electron will now have its own wave function. And we know that the kinetic energy can be written in terms of the wave function. So that was the main problem. So now each electron will have its own wave function, and you will be able to write the non-interacting kinetic energy of the total system as the sum of those individual electrons' kinetic energies. And this will be known as TS. S is for non-interacting kinetic energy. And then you will solve a Schrodinger equation kind of thing that is called Kohn-Sham equation. So it is similar to Schrodinger equation. That is, you have your Kohn-Sham Hamiltonian, then you have the wave function of each electron. So you will solve n equations for n electrons. So you have the non-interacting kinetic energy and then the Kohn-Sham effective potential. Now, this energy function that I already showed earlier. So earlier I just said this was a kinetic energy term, but now we have now further decomposed this kinetic energy. So now we have decomposed it into a non-interacting kinetic energy that I have shown here. So that comes from the individual kinetic energies of all the electrons. And then we have this unknown kinetic energy, that is Tc of rho. And that can be written as the difference of the exact kinetic energy of the total system that we don't know how to calculate in terms of electron density, and then this non-interacting Ke. So right now, if you see at this equation, we now know how to write the first term, the third term, and the fourth term in terms of the density, but we still don't know how to write Tc of rho and the non-classical electron interaction of rho in terms of density. And this is where if you have heard this term exchange correlation functional, so this is where it comes into the picture. So this kinetic energy, the small remaining kinetic energy that we haven't accounted for, can be said to be accounting for the correlations in your system. And this term, the non-classical electron-electron term, comes from the exchange interactions. So therefore, you can club these two terms together to write your exchange correlation functional. And then, so whatever we don't know, we just club it into the exchange correlation functional, and then our total energy functional looks something like this. So we have the non-interacting kinetic energy, nuclear electron interactions, electron-electron Coulomb or electrostatic interactions, and then the exchange correlation functional that consists of the small portion of kinetic energy that we didn't account for, and the non-classical electron-electron interactions. Now, this quantum DFT, although it is still quite cheap, it's not that cheap as the Thomas Fermi approach, or the where you wrote everything in terms of density. So now, since you have introduced orbitals, it has a scaling of n cubed. So if your system size is double, the computational time would be 8 times of the original system. So that is what this means. And you can routinely use it for systems with up to thousands of atoms. And this is when you're using the LDA and the GG approximations for the exchange correlation functionals. So what I mean by that is that in the LDA approximation, you just use the electron density to calculate the exchange correlation term, while in the GG approximation, that is the generalized gradient approximation, you also employ the gradient of the electron density to calculate the exchange correlation functional term. However, when you're using these simplistic exchange correlation functionals, sometimes there is a problem that you underestimate your band gap. And therefore, there is a lot of work always going on in coming up with suitable approximations for the exchange correlation functional term. We don't really know it exactly, so we have to come up with approximations. And this is something known as the Jacob's ladder. So essentially, the lower you are, the less accurate you are, and the higher you are, the more accurate your simulations are. And so in the first rung of the Jacob ladder consists of the LDA approximations for the exchange correlation term that only employ the electron density. Then GGA employs gradient of the electron density as well. Then you have the meta GG exchange correlation functions that employed the Laplacian as well as the kinetic energy density as well. And then you have the hybrid functionals that also employ the exact Fock exchange and so on. And as you go up the ladder, you get better band gaps. However, your computational cost starts to increase. So that is a problem. So you have to find a balance between computational cost and efficiency usually. Now, why is DFT so popular then? So because, as I mentioned, DFT provides you a very good balance between the accuracy and computational efficiency, and you can use the same DFT code for a lot of materials. It's not like for this material you have to use this thing, for another material to use another thing. No, you can, with DFT, you can simulate a lot of different materials. And the quantum equations are actually very similar to your Schrodinger equation, as I already mentioned. So it is really easy to grasp, understand. You don't deal with very complex equations, and it's quite reliable. And there are a lot of software available that are open source, and so you don't really need to spend a lot to start your DFT simulations. And since it is so old, there is so much tools, and so many tools and libraries that have been created with the focus on DFT that you really don't feel alone when you dive into DFT. You feel there is a lot of forums and literature and resources available online. And in fact, it is so popular that if you look at this, the number of publications that have cited some of the major DFT codes in the last 2 decades or so, you will see that these days we are reaching around, so at least in 2019, the number of publications was around 15,000, and these days it could very well be in 20,000 or something. So yeah. Next, I would like to talk about a very practical concept in any DFT calculation that you will be performing. So I already mentioned that you will be solving these quantum equations that are akin to Schrodinger equations, but you will be solving them for n electrons. But how actually you will do the simulations, so that is what I'm be talking about here. So with DFT, the most basic thing that you want is to get the ground state electron density as well as the energy of your system, right? So in order to calculate this ground state energy of any chemical system, you will need to specify a geometry for your code. So you will have to specify the atomic positions as well as the lattice parameters in case you are doing solids or material like periodic systems. And then you will have to come up with an initial guess. So just like any other numerical method, you will have to come up with an initial guess for your density, and then you will calculate this Hamiltonian or the quantum effective potential, and then you will solve these quantum equations for n electrons. And then when you solve these, you will get the orbital coefficients for these n electrons, and you will use that these n electron wave functions to construct the electron density of your total system. And you will check whether this new density versus the old density, are they changing a lot or not. And if they are not changing, then you can say, okay, my SCF is converged. Otherwise, you will repeat this procedure iteratively until at least your energy is converged or density is converged. Ideally, you should converge both of those. And once you have your converged density, then you can calculate forces on the atom, stress, orbitals, etc. So yeah, so now I will talk about this Quantum Espresso, which is a DFT code. Now, Quantum Espresso, the best part is that it is open source, and it has been developed for many years, so it is quite robust, and it has a lot of support online. So if you Google it, then you will find tons of resources and YouTube tutorials. So it's really easy to get started with Quantum Espresso, and it's quite efficient as well. So it's not like just because it is free or open source doesn't mean that it's slow and not as good, but it is actually really fast. And it mainly it is meant for periodic systems, so you can simulate 3D solids or monolayers, that is, or surface that are 2D periodic systems, or a nanowire that is a 1D periodic system with it, and it uses plane wave basis. So since plane waves are inherently periodic in nature, that is why it is suitable for periodic systems. And with it, you can, of course, calculate ground state properties like energies, or you can calculate band structure density of states to look at the electronic structure, and you can relax your geometry. So basically, maybe the starting geometry that you provided is not the ideal geometry. So you can, so probably it doesn't lead to an energy that is the lowest energy possible. So you can optimize the geometry as well. Now, there are other DFT codes as well, just to give you some ideas. So whenever you're working with Quantum Espresso, you will definitely hear about WASP at some point or the other, but it is a commercial software, so you will have to pay for it. It is very similar to Quantum Espresso, as it is also employing plane wave basis, and it is suitable for solids. And next you have TurboMole, which is again a commercial software, but it is not that expensive, and it employs a Gaussian basis actually, and it is suitable for both molecules and solids. And this is what I've worked with during my PhD. And then you have PySCF again, which is open source, so that is a very good thing, but here it is not very efficient. So if you compare PySCF with TurboMole, it would be like 10 to 100 times slower compared to TurboMole, but it is very similar to TurboMole conceptually, and it is really good to, if you're looking for a free Gaussian basis DFT code, then PySCF also does the job quite well. Now, what are the properties that you can calculate with DFT, right? So that is the main question. So at this point, you know, okay, I can do, okay, now you know that, okay, the main idea behind DFT, that is you employ electron densities, and you know that you will be using quantum espresso at least for this first session. So you know that, okay, it is suitable for periodic systems, but and I also mentioned some point that you will be calculating the ground state energy. But what does it help? How does it help me? How does calculating a ground state energy or density help me in doing computational material science? So that might be a question that you may be wondering about. So here are some of the very limited applications that I've mentioned. People do really amazing work with DFT, but here I have mentioned some of the very simple things that would be easy to understand, at least for this tutorial. So you can calculate the cohesive energy of your crystal. Now, cohesive energy basically indicates how stable is your material. If you have a high cohesive energy, that means, okay, it is quite stable. If you don't, then whatever, that means that this crystal that you are trying to make isn't possible thermodynamically. So this is how cohesive energy can be used to get an idea that, so maybe you are designing a material or something and you want to find, can this material even exist? So that is where cohesive energy will help you. Then you have adsorption energy. So and also I would like to mention, so whenever we are calculating energy from DFT, that is not useful by itself, but once you calculate relative energies, then it becomes useful. So that is why I have mentioned cohesive energy and adsorption energies here, because they are relative energies. So you are calculating energy of one or two systems and then subtracting those, and then you get some difference, and that is essentially your cohesive energy or adsorption energy, and that is actually meaningful. So adsorption energy, again, it tells you how feasible it is for a molecule to adsorb on a surface, right? How it would be interacting with the surface, whether it will stick to it or not. So it is actually very useful for catalysis and surface chemistry, and it can help you again design better, maybe solar cells or something like that. So yeah, so that is another application. And just one moment, let me check something. Okay, yeah. Okay. And also, are there, so have someone posted any questions yet? Let me just check. Okay, yeah, so, and also I will maybe pause right now and ask you if you have any questions till now. And also you can, if you have any questions, you can just ask, unmute yourself and ask me in the presentation or any lecture as well. So are there any questions? Okay, so I'll assume that I'm doing a pretty good job of explaining stuff, which is of course not true, but okay. So yeah, so next, again, okay, so we have a question. Let me see. Yeah, Mridu Smita,
Hi.
please. Yeah.
Hi, this is Madhushmita. Can you hear me?
Yeah.
Yeah. So, I was wondering that DFT, like, can we have a control over, like, whether we want to use LDA or GGA, like,
Yeah.
when we use DFT, and how to specify that? Or, like, is it particular to the software?
No, yeah, so essentially, scientists, ever since like 1990s, they have been coming up with approximations. So so first we had this LDA approximation, then we had these GGA approximations. So as the scientists develop these approximations, the DFT codes, they also try to include that in their code. So maybe one scientist comes up with a very good exchange correlation function, then the all the soft DFT codes that exist, they will try to incorporate that in their software and provide you like a setting where you can choose whatever functional you want. And in fact, sometimes you will notice that some functionals are not implemented in the DFT codes because people are usually coming up with at least 5 or 7 functionals every year. So in that case, there is a really good library called libxc library. So this library actually records each and every exchange correlation function ever made, and it provides an interface to all the DFT codes that I've seen that usually now all the codes employ. So with that, you get access to like hundreds of exchange correlation functions. So Yeah, so that is, so you can of course choose whichever functional you like. Yeah,
Okay, yeah, thank you.
no problem.
So just one question, like even in so you meant to say that even in the same software, for example, Quantum Espresso, so we can have the choice for different exchange correlation functional, right?
Yeah, but in Quantum Espresso, there comes an additional issue of pseudo potentials that I haven't mentioned yet. So, so Quantum Espresso employs pseudo potentials because otherwise you will have to describe each and so as I mentioned, the quantum equations have to be solved for each and every electron, but for each and every electron, if you employ so many plane waves, then the computation becomes expensive. And it is already observed that core electrons do not really take part in your chemical phenomena. So only the valence electrons are usually responsible for chemical interactions. So Quantum Espresso employs pseudo potentials where you combine nuclei and the core electrons together, and then you calculate the interaction of the valence electrons with the core and the nuclei together. So this is known as a pseudo potential approach, and a pseudo potential has to be developed for the different exchange correlation functionals. So you cannot simply use one pseudo potential developed for LDA, then you cannot use it with PBE. So in that way, I'm not sure how much of a variety you would have with Quantum Espresso, but yeah, I mean, at least you can use some of the main popular ones easily.
Okay, yeah, thank you.
No problem. Okay, so if there are no other questions, then I'll continue. And yeah, so you can also do some defect studies. So for example, if you want to study how a vacancy affects your electronic structure of a material, or how feasible is it to dope an atom into your material, then again, you will calculate relative energies to calculate the doping formation energy, vacancy formation energy, and so on. Then, of course, the band structure and density of states would give you insights into the electronic structure of your material. And you can also study excitations and optical properties and calculate the absorption spectra. However, for this, you will need to solve the time-dependent quantum equations. So till now, I have been focused only on the time-independent equations. But yeah, it is also possible to do time-dependent stuff with DFT, and that is actually known as time-dependent DFT, so TD DFT. And yeah, so as I mentioned, so cohesive energy. So in this, in the first session, we will probably try to calculate the cohesive energy of, let's say, silicon crystal as an example, and it is given as using this expression. So it is the cohesive energy per atom is given as the total energy of your crystal divided by the number of atoms. So that would be the energy per atom, yeah, right? So bulk refers to the fact that I'm calculating the energy of the 3D periodic crystal. So so to get the E bulk per atom, basically I will calculate the energy of the total system divided by the number of atoms, and then subtract the energy of the isolated atom. So in case of silicon, I will calculate the energy of the total silicon crystal, divide that by the number of atoms, subtract the energy of the single silicon atom, and I have introduced this negative sign here just as a convention. I mean, if you know your conventions, then you don't really need this sign. You can already tell if the cohesive energy means that your material is stable or not. But anyway, this convention will become clear more when we perform the simulation. But yeah, so this essentially tells you the energy required to disassemble your solid into its constituent free atoms, right? So this is what we will calculate in the first hands-on session, and also the adsorption energy that we'll probably do in the next session. So the adsorption energy again will give you the change in energy when a molecule or an atom is adsorbing on top of surface. So again, you will calculate the energy of your total system that consists of the adsorbate as well as the surface, and then you isolated surface and the isolated adsorbate. And yeah, so that will give you the absorption energy. And in this convention that I have written here, because people employ an opposite convention as well. So in this convention, a negative energy will indicate that the absorption is feasible or favorable, while a positive energy will indicate that it is not feasible. So yeah, again, this can be used for designing sensors, for example, because in sensors, again, this is your main what you're studying is when your material is coming in contact with some gas molecules, then how, if you can calculate the change in absorption energy or some the electronic structure, then it can help you design sensors. Okay, and now I will be coming to a really useful and practical portion of my lecture. So whenever you are performing a DFT calculation, I already mentioned you need to specify the atomic positions and the lattice parameters in terms of periodic systems. But where do you get those, right? So you want to perform a calculation, but I say, okay, first provide me the lattice parameter, and then you will maybe go through a book and find the lattice parameter for silicon, but can you find it for all the materials in a book? Of course not. So this is where this materials project database becomes really handy. It has documented data of about more than 100,000 3D materials, and I think more than 1,000 molecules as well, although it is more famous for 3D materials. And let me also go ahead and just share my full screen right now. So hold on a second. So yeah, so here is the materials project database. So what you can do here is you can, for example, here I have opened the silicon crystal, and you can find a lot of information about it, like the space group, band gap, predicted formation energy, so on. And here is how you can obtain the structure for your simulation. So you will click on export material details. Sorry, not this one, sorry. I guess here, yeah, export as. Yeah, so here you can get your crystal information, that is the atomic positions and parameters, in various formats. POSCAR is used by WASP, and you can also get it in the CIF format, that is the crystallographic information file. And this is actually really popular for crystals, so you can just go ahead and click on it and download it. And then later on, I will show you how to use it for quantum espresso simulations. But yeah, so coming back, so yeah, so this is really cool. And it also has, like, already they have calculated band structures, density of states, and a lot of other properties. So you can always use this to cross-check your results, at least while you are learning. When you will be researching, then you will be using, of course, a new novel material that you may not find here, but at least for learning, it is very good to cross-check your findings with this database. Next, I have, I like to mention the C2DB database, because a lot of times maybe your research is about studying absorption on surfaces. In this case, you don't need 3D structures, but you need 2D structures. And again, you have a database for that. That is the computational 2D materials database. So you can click here, recent progress of the sorry, that is actually the paper, sorry. You can click here, so browse data. And then, for example, let's say we want to look at the boron nitride, or we want to get the structure of the boron, hexagonal boron nitride monolayer. So we can just go ahead and click on it and wait for it to load. And yeah, so here you see the structure. And once again, you can download it as a CIF file. So that is the crystallographic information file. And you can also observe various properties, such as the optical properties here. Like it says that the first excitation or the first absorption that can occur is at around 5.7 electron volts or something. So yeah, so this database is also very good when you're cross-checking your results while you are learning. So yeah, so this is another database that will come really handy during your research or studies. And so these two databases were for periodic systems, but sometimes you want to do calculations for molecules. In this case, you have this PubChem database, which is again really useful. And you can simply just type in the name of the molecule, for example, like benzene, and you can click over here on the first search result, go down, and you can come to the 3D conformer portion, and then you can click on download coordinates and then save this file. So for periodic systems, the preferred format was CIF, that is CIF. For molecules, usually XYZ is preferred, but sometimes SDF is also preferred. So you can just go ahead and download that or whatever you need. So yeah, so that is another database focused for molecules. And then I would like to mention about this PyMatGen library. So it is a Python library, and it's really, and actually this is what materials project uses under the hood. So this is actually really useful when you want to pass this CIF file that we just downloaded. So with this, you can pass this CIF file, create a structure, manipulate it, like create a supercell or something out of it, and then you can convert it to other formats as well, and do a lot of more stuff with it. So it is really useful when you want to incorporate something in your existing workflow. So yeah, so this you can also check out later on after the today's sessions. And then there is this another library, ASE. So with this, you can essentially use just Python to define your structure, and then you can use any of these. So if you have these software installed, then you can run a calculation using any of these software. So instead of writing a different input for each of the different software, you can just use a simple standard or a unified structure and use any of the software to calculate something or manipulate something. And again, this can do format conversions, and it can also help you automate a lot of calculations. Next, I'd like to introduce Vesta, which is actually really good. It is so easy to use. So for example, I already showed you that we downloaded these CIF files, right? So if I now open Vesta, and so here I have Vesta opened, and now if I go to my downloads directory and I just drag this file that I downloaded for the silicon CIF, then you can see I can right away visualize this. It shows me, if you go to the summary, it shows me the ABC lattice parameters, the volume, the space group, etc. If you go to the output, then you can also see the atomic positions. So essentially, it is using symmetry to place the atoms at different positions. That is why you only have one atomic position mentioned here. But yeah, so it is really good for visualizing as well as for modeling. So you can also, like, for example, select an atom and just go hit the delete button and delete and create a vacancy. So this is also really powerful tool. You can also create surfaces, monolayers, and a lot of other stuff with Vesta. Then you have JMOL, which I like because here you can use scripting. So if you, for example, perform geometry optimization, then you have the atomic coordinates for a lot of steps, and you want to visualize or create a movie of this optimization. Or for example, you are studying the absorption of a molecule on top of a surface, and it is coming slowly and slowly to the surface as the geometry is optimizing. Then you can create this animation with JMOL. So that is why I really like JMOL as well. And then I have also created an application called PrisX 3D Viewer. And unlike the other softwares that I showed, they render your molecules in a sort of a cartoonish format. But with PrisX 3D Viewer, you can create really high quality graphics for, when you're publishing a paper in journals. Then you can use this to create your graphical abstracts or journal covers, or especially for presentations and posters, you can create such graphics. For example, for this journal cover, I used this PrisX 3D Viewer to create this cover. And I also created this CRISX augmented reality application where you can visualize molecules or crystals in augmented reality. This can be used for teaching or when you are presenting a poster or something like that. So this is another tool that you may find useful. And coming to BURAI. So this is actually what we'll be using today mostly. So this is a GUI for Quantum Espresso. So this actually is really good when you want to create input files really quickly and you want to model like a supercell monolayer or surface, then also it works really flawlessly. And you can either run the simulation in BURAI itself, or you can just use it for creating input file and then running the simulation on a high performance computing cluster. So this is what we'll be using today. So essentially you can download BURAI from their website here. So you can go to the resources, and then you can download the executable for Windows. In my experience, I didn't find it to be working properly on Mac OS or Ubuntu, but if it works for you, it can be really useful. For Windows, it always works flawlessly, provided you have Java installed, and you can also download it from here as well. So yeah, so BURAI is really useful. So for example, here I have it already installed on my system. So that silicon CIF file that we just downloaded, right, from materials project, you can simply drag and drop it just like Vesta. And here you will get your file imported in BURAI. And now you can easily create input for Quantum Espresso. So for example, it will read in the Bravais lattice type, the lattice parameters, then you will have the option to specify the zero potential, the atomic positions. And if you click here, you will see the input file that it is creating for Quantum Espresso. So yeah, so it is actually really nice. And coming to the question that was mentioned earlier about the functional. So here is where you will specify the zero potential. And you may notice it says PBE here. Sorry. Just 1 second. So PBE is actually a GGA type of exchange correlation function. So it includes the gradient of the electron density as well. So when I specify this, Quantum Espresso automatically sets the exchange correlation function to PBE, because my zero potential is actually PBE. And as you can see that the available exchange, the zero potentials in BURAI are all PBE type, but perhaps you can download something else from the internet. And you can also specify the exchange correlation type here, but as you can see, nothing else is available except for PBE functionals. So yeah. And there are a lot of different kinds of zero potentials. Usually people prefer the PAW zero potentials these days, but I'm not really updated with Quantum Espresso these days because I worked with Turbomole a lot. So you may have to look into the literature, what people are using these days, but yeah, perhaps PAW should be good. So yeah, so this is a really nice GUI. And yeah, and so yeah, so once you import your CIF file, then you can, if you want to, you can make some changes in the lattice parameters or positions if you want to. Otherwise, you can simply click here, go to the SCF tab, and now you can essentially run your DFT calculation. So, but before you do that, you will have to be careful of some parameters that you will need to change here. And this is actually really important. So the first parameter is the cutoff energy for your wave function. And this will essentially dictate how accurate your simulation is and how time-taking it is. Because as I said, as your accuracy increases, the computational cost increases. Now, this cutoff for wave function actually depends on the zero potential. So we will come back to the geometry tab, go to the elements tab, and see that what is recommended for the zero potential. So it is recommended to use like a 44 Rydberg cutoff for this pseudo potential. So come back to SCF, set that to 44. And this was, I think, 225 or something. So let's just set it to 250. So this is usually 4 times to 10 times that of the cutoff for the wave function. And in case your pseudo potential doesn't specify the recommended cutoff, then you can still find that out. So what you will need to do is you will need to run a series of calculations with different cutoffs, and you will observe that after some point your ground state energy won't decrease by much beyond a certain threshold. And at that point, you can say, okay, this is probably converged, so I'll be using this cutoff. So this is really important to mention in your research paper as well whenever you are publishing. What was the cutoff value that you use? Because sometimes you may have used a very low cutoff value, which is not really accurate. So you should mention so that people can reproduce your results, and your cutoff should be converged. Then similarly, the number of K points will again dictate how accurate your simulation is and how costly it is. And again, you should use a converged number of K points. So you will calculate the energy for, let's say, 1 K point, 1 by 1 by 1 K point, 2 by 2 by 2 K point, and so on, and see until which point the energy keeps going down significantly, and beyond some point it will not go down very significantly. So at some point it will converge. So that is how you will decide the number of K points to use. But to be safe, we will just use a really large value, 8 by 8 by 8. I'm sure it must be converged by then. And in fact, whenever you are not so sure, you can just use a really large value here as well. You can just specify it to be 50. You can specify it to be 4, this cutoff charge to be 400, and then you're good to go if you are sure that these are really large values for the system. Then the last thing that you need to change is, since you already know that silicon is supposed to be a semiconductor, so you will specify the occupations to be fixed, not smearing, but rather fixed. So yeah, so this is these are all the things that you will need to. Okay, so I think I have a question. Yeah, sure. I have 2 questions actually. So please, just unmute yourself and please ask. Vijay? Hello? Yeah. Can you unmute yourself, Vijay?
Hello, sir. Good morning.
Good morning. Yeah, what's your question? I saw that you have raised your hand.
No, sir.
Okay, so it's okay. Then you can mute yourself. Okay, and I have a question from Sushma. That is, what about using Gaussian 09 and Gaussian view for DFT? Of course. So if you're using Gaussian, so I don't have a lot of experience with Gaussian, to be honest. But of course, if you are using Gaussian, then they have this visualization program for that Gauss view. So if I think that should be pretty good as well. But yeah, here I was just mentioning some of the free tools for specifically for Quantum Espresso. But yeah, so that should also do the job. Okay, so coming back to BURAI. So yeah, so I made these changes. So I changed the cutoff for charge, K points, and the occupations to be fixed. And now I can come to my this tab over here and just go ahead and save my okay, so I get this glitch sometimes, so I'll have to restart BURAI. Okay, hold on a moment. So I can just pick the zip file from the recently used files and then go to the elements, because I changed the pseudo potential type to be the PAW type. Let's say use this, then go to the SCF 50 400 Thanks. Now, if you go ahead and see your input file, so let me also cover some of the basics of the input file. So here this states what kind of calculation you will be performing, so that would be SCF. And another important thing is that you need to specify the directory of your pseudo potentials that you're using. So since I'm using this GUI, it already takes care of that. But if you use terminal or manually create input files, then you will have to specify the path of the pseudo potentials. So you'll have to download the pseudo potentials, place them in some directory, and specify the path to that. Then you have these system settings, for example, the lattice parameter. Then you have the cutoff for the density, cutoff for the wave function that we just set up, the Brouwer lattice type, number of atoms. So in this unit cell, you have 8 atoms. So you have 1 atom at the corner, and then the remaining are just the images of that. And then you have 7 atoms besides that. For example, you have 1 atom on these faces. So again, the remaining are just the images of that. So in total, there are 8 atoms in the conventional unit cell. So yeah, so then this you can for now ignore. This is related to when you are facing some problems in converging your SCF, but usually you won't face any problems with these defaults. So then you specify the grid of the K points. Then you specify the name of the pseudo potential that you're using, and then the atomic positions in angstroms. Okay, so then you can just go ahead and save your file. So let's call it SI test. And once you save this project, you can just go ahead and run it and select the number of threads, let's say to 4, and click on OK. Now, if you come back to the project, go to the results here, go to this log file, then you will see that your calculation has started. It is using 4 processor cores, and you will see what it has read for the lattice type and all other stuff like that. And if you reload it, you will see how the calculation is proceeding. So it is currently on the iteration number 1, and it will take a few moments to complete. So let's come back to the presentation. Yeah, so this is BURAI that we'll be using today. And yeah, so coming next to, yeah, so I have this YouTube channel called FizzWiz that you can search, and I post a lot of tutorials on computational materials science, especially DFT, so you can check that out. I already have like 18,000 subscribers, so maybe you can help me increase this number. And then I also have this blog that you can perhaps check out, where I post different kinds of posts related to computational material science. For example, this exchange correlation functional post. And yeah, so in conclusion, for this lecture, I have showed you the importance and the basics of DFT, covered all the fundamental equations, and introduced supportive libraries, tools, and databases. And with that, I would like to thank you for your attention. And I would now ask you to let me know if you have any questions, as well as try to open up BURAI if you already have it installed on your systems. And we will try to calculate the cohesive energy of silicon, or maybe we can skip. So the next session that we have for the cohesive energy, for the hands-on, so the first session ends at 11:20, and the next session goes on for 1 hour and 15 minutes. Okay, so I think we can cover the hands-on stuff in the next session. And right now we have like 20 minutes remaining, and I think I'll take that to further familiarize you with BURAI and quantum espresso. So if that is okay with you all, so, and please let me know if you have any questions right now. So then I will proceed with explaining BUR stuff you can do with BURAI, and then in the next session we will calculate the cohesive energy and the absorption energy together. So any questions? Okay, so I guess there aren't any questions right now. In the meanwhile, I can also, as Mridu Smita asked, how to specify the exchange correlation functional. So I can show that. So PWX is the utility or the executable or the module in Quantum Espresso that allows you to do these SCF calculations. So I'm just looking for the input description, and you will go to the first search result, and here you will find how to specify the exchange correlation functional explicitly, because right now it just picks that up from the pseudo potential. So maybe if I search somewhere here, then you can see that somewhere it has picked up the pseudo potential or not. Yeah, so here it picks up the pseudo potential, and the corresponding exchange correlation function is set automatically. But yeah, coming back to the input description, so I think you could specify this XC somewhere. Yeah, input DFT. So this is the parameter that allows you to specify whatever functional you would like. So you'll have to check out this file to see what are the possible values, but you can do like BBE, BLIP, and a lot of functionals have been implemented already. So you can choose one of those, but by default it is read from pseudo potential, because you should use the same functional as the one used to create the pseudo potential. So yeah, so this is the parameter that will actually go in the electrons or the system card. Let me see, just yeah, system. So it will go to the system name list. Okay, so, and by the way, this calculation is now complete, and we are actually
comes with the result analysis. So I always check.
Sorry?
What you might be doing also.
Can you please repeat? I couldn't hear. Hello? Okay, so I have a question, by the way, here. By the way, whoever asked this question, I couldn't hear previously, but I have this new question by Arijit Mondal here. So why the potential is pseudo? Why we call it pseudo potential? Yeah, okay. So because ideally you have this nucleus, and you have electrons around it. So you have core electrons, then you have valence electrons, and ideally all these electrons are interacting with this nucleus, right? So you have this nuclear potential term, and all of these are interacting. But now what we are doing is we are taking the core electrons out of the picture by combining that with the nucleus. So you have your valence electron, and now they will be experiencing an effective potential from the combined core electrons and the nucleus. So now you have created this effective potential. So you can call it sort of an effective potential method, or a pseudo potential, that it is you create a fake potential for your valence electron. So it is actually it is also known as effective core potential when you are using like Gaussian basis codes like turbomole, Gaussian, or pi-SCF. Then you will hear the term effective core potential precisely for this reason, that it is you create like an effective potential of your core electrons, rather than, because the Coulomb term, otherwise you will have to account for the Coulomb term as well for the between the valence electron, core electrons, and all of those stuff. But here you just create an effective potential and call it a pseudo potential. And okay, so coming back to this VURAI, so in the results, now I have 3 files. So the first file was my input file, the second file was the output file, but here this is something VURAI creates to give you a nice visualization. So you can see that the energy in Rydberg's is decreasing with each iteration. So you start with an initial guess, you obtain the energy for this initial density, then you obtain the new density for this iteration, then you calculate the energy for this new density, then you obtain the new another new density. So you keep on doing that until you see that now the difference between the energy is not very significant. So you can see that it is not changing by much. So then you can say that the SCF is converged. And the threshold for your convergence is actually in the input file here. So that is the point after which the energies don't change by more than 10 to the power minus 6 Rydbergs. You will consider them to be converged. So yeah, and you can obtain the energy from your output file as well by searching for this exclamation mark. And yeah, so you have this somewhere in the end. Yeah, here. So you have the total energy here. And yeah, so what else? So you can, at the end of the calculation, you can see how long it took. So it took like 1 minute wall time. Wall time is your real time that you experience. Then you also see the orbital energies for each K point. So the first gamma point, you see the orbital energies. Then for another K point, you see the orbital energy. So you can see that I have 1, 2, 3, 4, 5, 6, 7, 8 times 2, 16 orbital energies. That means I had 16 electrons being treated explicitly, while the remaining electrons were treated by this zero potential approach. So they weren't included in my calculations. So I have 16 electrons being treated exactly. And at each iteration, you can see by how much the energy changes compared to the previous iteration. So yeah, so that you can see. And what else can you see here? Let's see. You can see how they created the initial potential. And yeah, so that is mainly it. Okay, so yeah, so here it shows that the number of quantum states, that is 16. So the same thing that I also mentioned earlier. So we have 16 explicitly treated electrons, while the remaining electrons are just considered the core electrons. Those are also 16 or what? Sorry. Okay. So I made a mistake actually. So yeah. Okay, so actually there are 32 electrons being treated explicitly. So 32 valence electrons are being treated explicitly, but each orbital can occupy, or like 2 electrons can occupy the same orbital, right? The upspin and the downspin electrons can occupy the same orbital. So we have 32 valence electrons being treated explicitly, and the total number of electrons would be much more. So silicon has, let's say, hydrogen, helium, lithium, barium, boron, carbon, nitrogen, oxygen, fluoride, neon, sodium, magnesium, aluminum, silicon. So silicon has 14 electrons, right? So we have 8 silicon atoms, so that would be even like a large number. But out of those electrons, we are just treating 32 electrons explicitly. So yeah, so that is how you do the SCF calculation. And have there been more questions? Okay, what is the advantage of turbomole over quantum espresso? And by the way, whenever you ask a question, maybe unmute yourself, because otherwise I didn't realize that there were questions. But anyway, so what is the advantage of turbomole over quantum espresso? So as I mentioned, that quantum espresso is mainly suitable for periodic systems, but when you go to slightly less periodic systems, for example, here I have a 3D periodic system. So it will be, this crystal will be replicated along all the 3 X, Y, and Z directions. But sometimes you only want to study surface. In that case, what you will need to do with quantum espresso, I will come to the geometry tab here, go to the modeler, and then I will create a slab model. So I will, let's say, create a slab along the some Miller index. So I will specify 100, let's say, click on build. Okay, now what do you see? So it created this sort of a slab, and you can also increase the area, let's say, no, not this thing, this thing. So yeah, so here I've created sort of like a slab of silicon. Now, what you'll notice is VURAI has introduced this vacuum in these directions. So my slab is now essentially periodic in 2 directions, while in the 3rd directions, it is still periodic, but it replicates after a certain distance. So it doesn't replicate right after it. So otherwise it will just be a bulk system. So you introduce this vacuum that you can again adjust. So if I do it like this, then it again becomes a 3D system. But if I increase the vacuum, that means that this will be separated by its image by this distance, and therefore the interactions at some point they will become 0, and that is when you can say, okay, I have created a slab or a surface. And when you do this, you create this large supercell, and you end up with a lot of plane waves that are not really needed, but you end up with them, and they require more time for your simulations. So this is not a problem with TurboMole. In TurboMole, you don't really need to create this vacuum. You can just tell TurboMole that my system is only periodic in 2 dimensions, and that's it. And then it won't waste computational resources along this 3rd dimension. While in Quantum Espresso, let's say I wanted to just study a nanowire. In that case, I'll have to specify vacuum in 2 directions, and it becomes even slower. And yeah, so that is an advantage of Quantum Espresso. So you, sorry, TurboMole. So you will see that for a 3D bulk system, Quantum Espresso is much faster. While when you go to lower dimensions like 1D, 2D, then TurboMole becomes much faster. And especially for 0 dimension, that is a molecule or an atom. Okay, then the next question is, kindly throw some light on RMT, radius or muffin tin term in DFT. Okay, so unfortunately, I'm not really familiar with these terms actually. So sorry for that. And then there's a question, we need to get a test density, then V is a functional density, then how the new wave function can be obtained. Yeah, so coming to the, let's say, sorry. Okay. So this flow chart that I had over here. So your question is how the new wave function can be obtained. So yeah, so essentially what you do is you when you solve this Cornsham equation, you get these orbital coefficients for the individual electron wave functions, right? So once you have the, and these are known as Cornsham orbitals, right? So once you have these Cornsham orbitals, then you can construct the density, but you already have these Cornsham orbitals. So you start with the density, you solve this equation, and then you do get these Cornsham orbitals. And actually you write them in a matrix form. So you don't solve each and every equation individually, but rather you write these equations in a matrix form. And then once you diagonalize, so it becomes like an eigenvalue equation. So H psi is equal to E psi sort of thing. So you just diagonalize it, you get the coefficients of these Cornsham orbitals, and then you can write them in terms of a Slater determinant, but you don't really need the wave function in DFT, so that is not very useful. But yeah, essentially once you solve this step, you get the new wave function, and then you obtain the density from this new wave function, and then you sort of keep on running this loop. And what about, sorry, yeah?
Can you show the creation of nanowire just by introducing vacuum on both directions?
Yeah, so BURA right now doesn't have this functionality, but you can always do it manually by, okay, so nanowire, you will have to, yeah, so one idea would be to just open this Investa and go to unit cell, transform, create like a reasonably large supercell. Or maybe I can just create it like this. Okay.
We can't do it on both.
Yeah, this nanowire, I'm not sure if you can do it on VURA. It has this supercell option and slab model option. but let's try. Okay, so let me reinitialize, create a supercell in just one direction, let's say, build. So, okay, so I have this sort of a elongated system. Now what I can do is I can try to introduce a vacuum along the Y and Z direction by editing here. So I will choose the free thing here and then write 15, let's say, and 15. Yeah, okay. Yeah, this seems to work. Yeah, so yeah, okay, so let me explain it once again. Okay, so let me open this structure again. So let's say I want to create a nano, one doesn't do it for silicon, but rather carbon, but okay. So let's say I just want to create some 1D system. So I can create a supercell first of all, or maybe not even, it looks nice if I create a supercell. So let's say I will be elongating it along the X direction. So let's make it 3 times there and the remaining just 1. And then come back, yes, yes, and then go to the free Brovay lattice type and just increase this Y and Z lattice parameters over here. And this now has vacuum along 2 dimensions, and you can also come back to the modular. Ah, shit, it didn't save, or let me save it. And come back to the modular. This is strange. It isn't reflecting. Yeah, okay, I had to click on the initialize model. Okay, and now you can just translate it slightly so it looks nicer. So you can translate it like this so that it would be in the center of the cell, so you can have it at the center. And now you have vacuum along 2 dimensions. Yeah. So this is how you can do it in BURAI as well, actually, but you just have to do it by your own.
Can
So,
we
yeah.
publish this in our research papers?
This is just like I'm sure this structure is not correct. I'm not sure if SI has a 1D structure or not, but yeah, of course, I think carbon probably has a 1D nanowire structure, and then you can try to create it. I haven't really worked with 1D stuff, but this would be the way to create, but you will have to go through literature about how you can, yeah, okay, nanotube. So yeah, you will have to read more about it to know more.
Single CNT.
Yeah, but yeah, once you read the computational details of a paper, you will know how they created this. For example, I think this here they have explained that the carbon 1D nanotube is constructed from a rolled graphene. So this is again very difficult to do with BURAI. So I'm not sure if we can do it with BURAI. But yeah, for some cases, you just have to find the structure online. But if you know what you are doing, like which system you are studying, and it can be made like this, then yes, but I'm not sure. It will depend on the system to system if this structure is really 1D. It is found in nature or not. But yeah, this is how you will essentially create a structure that has 1D or 2D periodic boundary conditions. Yeah.
Okay, thank you.
No problem. Okay, next question is, what about MD simulations? How to specify ensembles here in the input file? Okay, so I'm sorry?
Just one query.
Yeah.
Number of Conchan states is same as the half of the number of valence electrons.
Yeah, yeah.
And this is what it is being showing on a K matrix. When it is, we are choosing different values of Ks. Okay, and those 16 values which are coming, the energy of the each orbital which is showing is these are these 16 Conchan states.
Yep. Yes. Yes.
And suppose my system is not reading band gap. So if I just subtract the the last negative and the first positive value, can I call it as a gap?
No,
After-
no, that you cannot do yet, because right now we only have the valence electrons included. So we have only calculated the valence bands. For band gap, we also need the value of the conduction bands energies as well. So for that, you will have to.
Negative. What is this positive value showing? Like,
Yeah, it is.
yes, it's
Yeah.
showing -6. Huh?
Yeah,
Then
and
positive.
but these
Isn't it
values don't
positive
really.
had- okay.
Yeah, but these values don't really matter whether they are negative or positive, because quantum eigenvalues don't really have like a physical interpretation in this way that just because it is positive, you cannot consider it. These are all values for the valence electrons, not conduction electrons. So even if they are positive, negative, it doesn't matter. But what you can do is you can. So we already checked that. We have 16 valence bands, right? So if I go to the band utility, then I'm just coming here because I need to see this parameter. It is called N band. Okay, so I'll just copy this N band parameter, come back to SCF, and just paste it here and specify it to be more than 16. So let's say 18 or something, and click here. So now if I calculate the SCF energy, sorry. Okay, sorry, I have changed the structure quite a bit, so this won't be right. Let me just quickly undo. Let's try. Can I? No, let me open it again. Okay, yeah. So coming here, band. The parameter was N band. Copy it. And so now let's just wait 1 minute, and in the meanwhile I'll answer another question. Yeah, so MD simulations, sorry, I'm not familiar or an expert with MD simulations, so unfortunately I can't help with that. And then how to export structure files in different formats. So yeah, so this is where ASE can really be useful. So it has a really nice module where you can convert your inputs to various formats or something. Yeah, so these are the formats that it supports. You can use ASE, you can even use Vesta, because it also can be used to export in various formats. So you have XYZ, Cube, VASP, so this can be used, but ASE would have the most comprehensive list of formats that you can use. And then okay, so yeah, so please keep your questions for the question. Okay, so yeah, so now this calculation is completed. Let's see, log SCF, and now actually you will see that it prints out the highest occupied and the lowest unoccupied level. And this, now you can take the difference of these two values to get the band gap. This you can call the band gap. So you have 6.72, 6.72 minus 6.13, almost, right? So you have a band gap of like 0.59, and which is actually in good agreement with the reported value in materials project of 0.61. So it's very close. The remaining difference could be due to the use of a different zero potential, and they use WASP. So maybe some other approximations. Yeah, so mainly this difference is pretty small. So yeah, so and you may wonder why this band gap is so bad, because silicon is supposed to have 1.2 electron volts, I think, band gap. But of course, as I mentioned, the exchange correlation functional is not very accurate. This GGA one, so you will have to use more accurate functionals. Okay, so. Okay, so I think this should be it for the first session, and in the next session, you can have your BURAI ready, and we can try to run the calculations for cohesive energy calculation and absorption energy calculation.
Thank you so much, sir, for the insightful lectures. Participants can now leave for a tea break for 10 minutes, and they are supposed to be for the next session at 11:35.
Yeah, thank you, Dr. Manas. Thank you so much.